Hi, I'm Vishal, and in this video, we are going over this November 2024 paper from HL Physics. It's it's paper 3, and before we go about solving questions from this paper, I just want to tell you guys that not all of the questions have been solved or attempted in this video because many of them are not a part of the current syllabus. So, having said that, let's get solving. So, this is our first problem, and if you have gone through it, so here's what we have. We have some students trying to figure out the relationship between the resistance of this wire with its temperature, and the data that they have collected has been plotted on this graph. The first part of the question requires us to draw a straight line through these points. So in order for us to draw the line of best fit, we need to make sure that the line passes through all of these error bars. So it should be within all of these error bars, and we have to make sure that it either passes through most of these data points or has data points equally on either side of these lines, both above and below. Okay, so we have completed this first part. Having done that, the second part requires us to do a gradient operation. So here we are required to find out the gradient of this best fit line. How are we going to do it? We have an expression that enables us to find out the gradient if we know the coordinates of 2 points on this best fit line. Now, while selecting 2 points on this line, make sure that you are not considering points that are actually from the dataset, because sometimes they might appear to coincide on this line, but they might not be. Hence, I'm going to take 2 points, one somewhere here. I know it's a bit off, but okay, let's say that's the first point, and the second point be somewhere here. And the coordinates of these 2 points, so the first one has the x coordinate somewhere here, and this major segment has been divided into 5 minor segments. So it's 20 divided by 5, which is 4 degrees Celsius for each minor segment. So 4 degrees Celsius, and at that temperature, the resistance is 6 ohms. So that will be our first coordinate. Oh, sorry, the coordinates of the first point. And for the second point, we have 60, and I need to draw a straight line if I'm not sure where it's going to coincide or where it's going to intercept in the vertical axis. So it's somewhere near 7.2 ohms. There we go. We have 2 points and we have both of their coordinates figured out. Substituting these coordinates, we get 60 minus 4. You might have noticed that I am not writing down all the units here because I want to keep my calculations a bit neat, but I will add the units at the end. Okay, so I have already calculated the value, so it's this one. I'm going to write an approximate value of that calculated figure. So it's 0.021, and its units will be ohms per degree Celsius. Why? Because in the numerator we got everything in ohms. So, and in the denominator we have these two numbers in degrees Celsius as well. So their difference would also be in the same units. Fine. So we got our gradient value, and now we have to find out alpha, and after doing that we have to assign it a unit as well, a unit that's consistent with this equation. So let's compare this equation with the equation of a straight line, the general equation. That's y equals mx plus c, and I'm going to write down this equation as well. Let's multiply r naught inside of these parentheses. So we get r naught, and I'm switching the terms inside of this parentheses. So r naught alpha theta plus r naught. So comparing these two equations, we find out that m, which is the gradient, and it's equal to r naught alpha theta, and c, which is the intercept, to be r naught. So in order for us to find out the value of alpha, we're going to make use of this expression. Lambda, there is no theta here because I need to take the coefficient of the variable. So the coefficient of variable is r naught alpha, and that equates to m, the coefficient of the variable x. So theta is the variable and r is another variable. So they are both equivalent to x and y. The coefficient of x, m, is equivalent to r theta alpha, r naught alpha, sorry. So r naught times alpha, and alpha becomes m divided by r naught. So m is already there, 0.021, but instead of taking this approximate value, I'm going to take the exact value that's obtained by calculation. So now the only thing left is to find out what r naught is. How am I going to find it out? So I'm just going to use the fact that it's the intercept of this line. So the intercept is 5.9 ohms, and I'll substitute that here, 5.9 ohms. You can write down the units at the end as well, so that's not a problem. So this is our answer. What would be its units? In the numerator we have the gradient, which has the units of ohm per Celsius, and in the denominator we have r theta, which is a value of resistance, so it's expressed in ohms. Theta gets cancelled out, so what remains is per Celsius. So that's the value of alpha, and we can actually find out the unit of alpha in a very different manner by using this equation. So if you look at this equation, we see that there is one term which is just a number which doesn't have a unit, and the other term which is being added to that number should also be unitless. The product of alpha times theta, the product of alpha and theta should be unitless as well. We already know that theta is temperature and is expressed in Celsius. So what should be the unit of alpha if multiplying this with theta would give us a unitless quantity? Well, it should have a unit which is inverse of the unit of theta. So if theta has a unit of degree Celsius, alpha will have a unit of per degree Celsius. This is the second question, and at this point you can pause this video to have a look at it. Okay, so what we have here is a small ball that's released alongside this meter scale, and we have clicked 4 photographs of this small ball and laid it alongside each other so that we get 4 different positions of this ball at the same time. The first part of this question asks us to determine the value of g using these photographs, and we're also given this relation. So we can rearrange this relation to get g equals 2s divided by t squared, and we need to find out the value of s and t in order for us to find out the value of g. So what is s? S is the distance through which the ball's fallen. So to find that out, we need to mark 2 positions, the initial position and the final position through which the ball is falling. We can take the initial position to be the release position at time is equal to 0. So the final position can be any one of these 4 instances. So I'm going to take this as my final position, the last one. In order for us to mark the position of this ball relative to this meter ruler, I need to draw a line so that it coincides with one of its major or minor ticks. So if I choose to mark it at the bottom of the ball, I need to be consistent throughout my markings. But I'm gonna choose the position of this ball to be somewhere at the midpoint. So in that way, the initial position would be somewhere at 5 centimeters. Yeah, so this is 5 centimeters here, and the reason why it's in centimeters is because this is a meter ruler and every major segment is a centimeter and every minor segment is a millimeter. So the initial position is at 5 centimeters and the final position would be close to 24.5. The difference between these two measurements would give me the value of s, which is 19.5 centimeters. So we got the value of s. Now we need to find out the value of t. T is measured in seconds. So we need to find out the duration between its initial and final position. Its descent from its initial and final position. Yeah. We need to keep in mind that all of these photographs are 0.05 seconds apart. So we have 4 such photographs, and the 4th photograph is my final position. So the total time that has elapsed when this ball falls from its initial position to its final is given by 0.05 times 4. That would be 0.2 seconds. So time taken to cross this distance is 0.2 seconds. And this is not just any distance, but the distance from its release position. Okay. And I can substitute that into this relation to get the value of g. So it's 19.5, and if I convert that into meters, I would get 0.195. Divide that by 0.2 squared, and I have already calculated the value out. It comes out to be 9.75 meters per second squared. Meters per second squared because it is the value of acceleration. So acceleration is measured in meters per second squared. Yeah, and I have made sure that the quantity that I have used to calculate this g is also in SI units. So I have converted this distance from centimeters to meters. Converted it. Yep. Okay, so we got our value for g. Now we need to find out the absolute uncertainty in g. So that would be delta g. But before that, we need to calculate the relative uncertainty. So making use of this relation again, I can write down delta g by g, or the error in g divided by g, is equal to delta s by s plus 2 delta t by t. So where's this 2 coming from? It's because there is an exponent for t. So while multiplying, the uncertainty just adds up. And yeah, so the percentage uncertainty is already given. So that's what we are adding here. But before that, we need to find out the absolute uncertainty of t. So what's that? Plus or minus 5% of t. And t is 0.2 seconds. So 5% of that is 5% of 0.2 is 0.01, and to multiply that 2 times. So 0.02 divided by 0.2. So we have that term substituted and also a bit simplified. Delta S, the absolute uncertainty in S, because we are using a meter ruler and the least count of this meter ruler is 1 millimeter. So we can just simply take that as our uncertainty. I'm going to take 1 millimeter, which is equal to 1,000 of a meter. So I'm going to take that as it is, or else, so this is 1/10, 100, and 1,000 of a meter. Divide that by the actual measurement. So what's obtained? So it's 0.95. Okay. I'm going to simplify this using my Desmos calculator. And the other term is 0.02 divided by 0.2. So we get 0.15. I'm just going to write that down, 0.105. But this is not the actual absolute uncertainty. So we still need to rearrange this equation and substitute for g to get delta g. And the value of g obtained in the first part, in part A, is 9.75 meters per second squared. And instead of using an approximate value that I have noted in that part, I'm just going to multiply this whole thing by 9.75. So in that way, I get 1.025. So delta G is equal to 1.025. And the error is just the difference between the actual and the true value. So the units for the error in the quantities will also be of the same meters per second square. Okay, now we move on to the final part. suggest a suitable value for the maximum duration of the flash. Fine. So we need to find out the maximum duration of the flash. What's a flash? A flash is something that says for how long the camera captures the ball. So we might have thought that the camera captures an instant of the ball's journey, but it's not an instant, but it's a duration. So this needs to be as low as possible so that we get an accurate measurement of its position. But we already know that the measurement, the uncertainty in its position measurement is 1,000th of a meter, because the meter scale, the meter ruler, is accurate to 1 millimeter. So we need this flash, this photograph flash, to produce an error in its position which is equal to this, equal to or less than this. So the time duration in which the flash is on should produce change in its position of about 1 millimeter. So we need to find out how fast it's moving, or its fastest velocity in all four of these instances, or in all four of these positions. And it's fastest at its most bottom position. So I'm going to calculate the velocity at this point. I can do that by using v square is equal to u square plus 2as, which is one of the Stewart equations. And the final velocity is what we need to find out. Its initial is just 0 because it was released from rest. And 2 times a is found out to be 9.75, which is not the usual value, but this is what we have found out. So we're going to make use of that. And s is the total displacement, or the distance from its release position to its final position. So it's 0.95 meters. Okay. So we need to multiply all these things and then take the square root of everything. So square root of 2 times 9.75 times 0.195. Is that what it is? Yes, it's correct. So we're getting 1.95. So that's how fast it's moving at its final position. So it's the highest velocity that this ball can have, and during which, if the flash is turned on, it should be only turned on long enough so that it covers 1 millimeter or less. So in order to find out the time duration for this ball to travel 1 millimeters, I'm going to make use of this velocity formula. Velocity is equal to displacement by time. We can assume that this ball is moving at a constant velocity for an infinitesimal amount of time. So we're going to see what that is, or how much that is. So 1,000, this is how we write 1 millimeters in scientific notation, converting that into meters. Okay, and I have only done this because the velocity is in meters per second. So I need to be consistent with units, otherwise I'm going to get some error because of that. Okay, so this is what I got. And I'm going to use the calculator that's provided here. 1.95 meters per second, and on the top I have missed 10 raised to minus 3. Okay, so this is what I got, 0.00051. Let's keep it as it is. 5 seconds. This is the most amount of time in which the flash can be turned on. So if it's any longer, we will get an additional error because of that in its position measurement. Okay. So this is the third question. You guys can take a look at this question, going through its details carefully. So, okay, here we have two objects P and Q, and P is transmitting a radio signal towards Q. Q itself is at rest relative to the Earth, and P is moving at the speed of 0.70 times c, where c is the velocity of light in vacuum. So it's just 70% of the speed of light, or velocity of light. So using the Galilean relativity principles, we had to find out the speed of this radio signal coming out from P as seen from Q, relative to Q. Now, according to Galilean relativity, if something's moving inside of a moving frame, the thing's velocity is not just as seen from the moving frame itself, but if W is the velocity of the moving frame, and if V prime is the velocity of the object as seen from this moving frame, the velocity of that object as seen from a rest frame in which the velocity of the moving frame is W is this, the sum of the velocity of the two the sum of the velocity of the object and the frame itself. This is also known as the theorem of addition of velocities in Galilean relativity. So using that, we can find out the velocity of this radio signal as seen from Q. So the velocity of P, which is 0.70 times c, and V prime, which is the velocity of this radio signal as seen from P, is c. So V, which is the velocity of this signal according to Q, is equal to 0.7 times c plus c, just gives us 1.7 c. Okay, so using Galilean relativity, this is what it comes to be. And we are going to determine the exact same thing, but we're going to use the relativistic velocity addition. So according to the theory of relativity, we not only have to add the two velocities, but we also have to do something extra. And this extra thing comes from the fact that lengths and time intervals adjust themselves to make the speed of light a constant, to keep it as a constant. And I'm going to tell you what that is as we visit the third part, the last part of this question. So V prime is 0.7 c again, and W is same, c. So I'm gonna put the exact same values below as well. C square. Simplify this equation. I have 1.7 c at the top and 1 plus 1.7 at the bottom, because there are two c's here and there's a c square at the bottom, so it gets cancelled out. What remains is c. So the velocity of this radio signal as seen by both a moving observer, which is actually emitting this radio signal, and the ones which is at rest, is exactly the same. So, and it should be, because that is one of the principles of special relativity, one of the postulates. And paradigm shift. Let's talk about the last question. So Galilean relativity was replaced by the special theory of relativity, fine, given by Albert Einstein. Explain how this paradigm shift was linked to Maxwell's discovery. Yes. So the second postulate in the special theory of relativity was actually a discovery by Maxwell. So Maxwell's electrodynamics actually predicts that the velocity of light in vacuum is pretty much a constant. It's independent of the frame in which it's observed. So whether the frame is moving or not doesn't really matter there. And it doesn't, well, by that, it also means that it's independent of the source, the motion of the source too. So whether the motion is moving or at rest relative to something else, um, the source which is actually producing the light and the ones that's actually observing the light, both of them will see the exact same speed, which is c. So that's something right there. And I think because of that, we got something called the Lorentz transformation to basically keep the velocity of light essentially a constant, going from one frame to another, making transformations so that the velocities transform in a way to give out the exact same value c. Okay, so that's how we write it down. We can add more points to it, but yeah, we just say that Maxwell discovered that the velocity of light is essentially a constant when it's in vacuum. Of course, it's independent of its frames, so we can mention all those things here. Okay, so we have the fourth question with us, and you may pause the video and read through this section to understand the details of this question better. So we have a space station, and within this space-time diagram, it's described by this whirl line, this vertical line which passes through the origin. And we have two clocks on either side of this space station, which are equally distanced away from it. There is also a spaceship that's departing the station at time t is equal to 0. This is the whirl line of that spaceship. We also have an event that's marked on this diagram. So we may expect a question referencing that. But in the first part, we need to find out a way to synchronize these two clocks with another clock on the space station. One way of doing it is to have all these three clocks at the origin when time is 0. We set the time on all these three clocks to show the exact same thing. Then we make them to start working at the exact same time, so they're all synchronized. Now we bring these two clocks back to their original positions, but while we are doing it, we need to make sure that these two clocks don't have velocities which are comparable to the speed of light, because if they're moving with a relativistic velocity, there will be time dilation which is going to slow down the rate at which these two clocks are working. So when they go back to their original positions, they might not be showing the exact same time as the one that's shown on this clock on the space station. So in question 2, we need to find out the relative velocity of the spaceship A. So how do we do it? So velocity of A relative to S. So here we have the whirl line, and whenever there is a whirl line of an object which is moving relative to the whirl line of another object, we need to measure, or we need to calculate the gradient of the whirl line of that moving object relative to the spatial axis according to which we are trying to find out the velocity of. So here it's the spaceship whose velocity we are trying to find relative to this space station. So we need to find out its gradient relative to this spatial axis. So in order for us to find out the gradient, we first have 2 points on the vertical axis. It's 8 and 0. What about 2 points on the horizontal axis? It's 0 and 2. So the gradient of the whirl line of A is 8 divided by 2, and it comes out to be 4. So in order to find out the relative velocity, we make use of this gradient and we invert its value. So we don't need the gradient itself, but we need the inverse of it. And since c is already present intrinsically in the time axis, we need to make sure that we multiply c while we are finding out velocity. So it's 1 by 4 times c, which is 0.25 times c. So 25% the speed of light. That is the relative velocity of A according to S. The third part says that the two clocks emit separate light signals when A is at 0, and just keep in mind that these two light signals are emitted simultaneously from clock 1 and clock 2. Identify on the diagram the proper time that elapses between these two signals. Okay. So we need to draw two lines which represent the world line of light that's being emitted by these two clocks. So I'm drawing one of these lines which intersect the world line of A at some point, and another line coming from clock 2 which also has a gradient of 1. Why do we need to have a gradient of 1? Because it is describing light. Although these lines might not be perfect, you guys need to make sure that the gradient of these two lines be equal to 1. Otherwise, they wouldn't be describing light. Okay. So these two light signals meet A at two different times, at two different events in the space-time. So I'm marking these two events by a red dot. And the time that has passed between these two arrivals is a line that's going down vertically according to S. But if it's according to A, you need to draw a line on this world line of A itself. Okay, so that's done. Let's move on to part B. So in part B, they're saying that there's another spaceship P that leaves S at event E and then intercepts A. The speed of P is given to be half the speed of light, so its gradient in the space-time diagram will be twice as that of light, so it should be 2. Then we need to identify the point at which P is intersecting A on the world line of A. So let's do that on the space-time diagram. We need to draw a line that comes out from this point E and intercepts A. But we need to make sure that its gradient is 2. Okay, here we have it. I'm going to mark it with a green dot. So coincidentally, we have already marked that dot to find out the gradient of A relative to the spatial axis of the space station S. So that's the point at which spaceship P is intercepting spaceship A. This is the world line of that spaceship P coming out from event E, coming out from S at event E. So we need to mark that with the letter X. And for the second part of the question, we need to find out the time of event X relative to the second clock. So it's really just 8 seconds. CT is given in kilometers, but when we convert that into seconds, it would come out to be 8. So it's 8 seconds. And in the last part of the question, we have that spaceship A coming back to the station, and they have constructed the frame of the space station as it moves. So we have two frames, the primed frame and the double primed frame as it comes back. So this is the point where it makes a turn, spaceship A, and this is the point where it's returning to the station S. Now we need to identify with lines and labels T1 and T2, which is the time that's elapsed for this space station. T1 is the time immediately before the spaceship changes its velocity, and T2 is the time immediately after it's changed its velocity. In part C, we have this spaceship A coming back to S, space station. So they have already constructed the frames for spaceship A as it leaves and returns to S. So we have two different frames right here. The primed frame, which represent the spaceship leaving S, and the double primed frame, which represents the frame of the spaceship, which is returning when it's returning to S. So this is the point where it makes a turnaround, and this is the point where it's arriving back at S. So we need to find out the time right before it made a turnaround and right after it made that turn. So in order to mark these two times relative to S, so within the frame S, we need to mark these two times. So it's marked as T1 and T2. So in order for us to do that, we need to draw two lines which are parallel to X prime and X double prime. How do we do that? So I'm gonna draw a line and then have this line move here, also maybe shorten a bit without changing its angle. So draw a line at the point of the turnaround which is parallel to this X prime. So that becomes my T1, and the time right after the spaceship A has turned is a line which is parallel to X double prime. So I'm going to draw it right here and see if it's parallel. I can then place it right here so that we have an extension of this axis which intercepts the vertical line, which is the vertical line of the spaceship. So this is T1 and T2. Although it's the exact same point where the spaceship made a turnaround, there is a difference between the times right before and right after it made that turn. And the second part is asking us how we are seeing this difference. It is because when the spaceship made a turn, it jumped from one inertial frame to another inertial frame. So an object cannot turn without accelerating. So when it accelerates, it changes its inertial frame because its velocity has changed now. So that's the reason why there is a change, or there is a difference between these two times. And this is also the reason why that within this twin paradox that we have heard, we see a difference in the age of the two twins. Okay, this is our fifth question. So go through this question carefully, taking your time. So let's take a look at all the information that's given here. So we have a bunch of muons which are created at this height above the Earth's surface, which is 2.5 kilometers. So I'm going to convert that into meters because we're going to need it like somewhere in our calculations, I suppose. And its velocity as it comes down towards the Earth is 0.975 times c, where c is speed of light. So that's our velocity. And we also have the average lifetime of a muon in microseconds. So I'm going to convert that into seconds. Mu is micro in this context. And this measurement of time is done in a frame where muon appears to be at rest. So you can also say that it's the measurement of the time measurement is done in the muon's own frame of reference. And in part A, we are required to calculate the mean lifetime of a muon in the Earth's frame. So in the Earth's frame is where the muon is moving with the velocity of v. So I'm going to make use of that information to calculate this gamma factor, which is 1 minus v squared by c squared in the denominator. Then we have to take the square root of that. Substituting for v, we get 0.975 squared times c squared divided by c squared. C squared gets cancelled out, and what remains is this. So I have done the calculations here, and it comes out to be 4.5 approximately. I'm just keeping two significant figures after the calculations. Okay, so let's make use of this gamma factor now. We know that when things start to move, they experience time differently, and when time is measured from a moving frame, it undergoes time dilation, and the equation for that is given by t is equal to gamma times t naught, where t naught is the time measurement done in a frame which is at rest, and t corresponds to the same time, but yeah, it's measured in a moving frame, so it will get dilated, the time for the same event, but it's a bit dilated, and now it's larger than t naught. Let's see how large it is. So 2.2 microseconds times the gamma factor, 4.5. Let's plug in the average lifetime of a muon as seen from the muon itself. Now it's been dilated to 9.9 microseconds because we have 6 digits after the decimal point. Well, more than 6 digits, but yeah, we can have 9 as our digit before the decimal point, so it becomes microseconds. Okay, so yep, in part B, we have to show that this serves as an evidence for time dilation. And there is also this fact that's given here. Muons are detected at the Earth's surface. We need to show that this is only true if time dilation occurs. So let's try to find out the time that's required for these muons to travel this distance of 2.5 kilometers. Okay, so in order for us to do that, we divide the distance 2.5 kilometers, and I have converted that into meters by its velocity, which is 0.975 times 3 times 10 raised to 8. And I have done the calculations for that as well. So here we go. Again, we have 5 zeros until we reach the first non-zero digit. So it's 8.5 microseconds, which we can also write it down as 8.5 milliseconds or microseconds. So a muon requires this much time to travel 2.5 kilometers with this velocity, but if time dilation didn't occur, it would die way before it reaches the surface, because its average lifetime is just around 2.2 microseconds. So time dilation has to occur if we are to detect it at the surface of the Earth. Fine. Okay, we have the sixth question with us right now, and for this question, we have the kinetic energy of these muons are related to their gamma factors by this straight line that's plotted in this graph, and we are required to calculate the rest energy of these muons. Okay, so the gamma factor is calculated using this expression, and for the rest energy, we need to find out the difference between the rest and relativistic energy expression. So if this is the relativistic energy and this E0 is the rest energy, its difference is what we call the kinetic energy. So at least that is what is true in relativistic mechanics. So when objects speed up, their kinetic energies increase, but with that their mass also increases. So m is our relativistic mass and m0 is our rest mass, and the relativistic mass can be expressed in terms of the rest mass and the gamma factor as m0 times gamma. Factoring out m0 c square, I get gamma minus 1 is equal to ek. I can rearrange this equation to get m0 c square, which is the rest energy, as kinetic energy divided by gamma minus 1. So here they're asking us to find out this E0. We can substitute any value for Ek, and if we substitute the corresponding value of gamma, we will get m0 c square, the rest energy of the muon. So I'm going to choose 1, I'm going to choose 2 for gamma, because we cannot have 0 in the denominator, and it makes it easy for me to calculate this rest energy if I have a unit in the denominator. So for a gamma value of 2, I will have 110 as the kinetic energy. So 110 MeV, mega electron volts of kinetic energy. Divide that by 2 minus 1. I'm substituting 2 in place of gamma. So the final answer is 110 mega electron volts. This is the rest energy of the muon. Okay, so let's move on to part B. So muon has the same charge as an electron. So we have to deduce the potential difference required to accelerate this muon from a velocity of 0 to a velocity of 0.96 times c. But one thing to note here is that the energy that's obtained from this potential difference that accelerates this muon from a velocity of 0 to um, a velocity of 0.96 c will all be stored inside of it as its kinetic energy, because the energy that this muon obtains will only increase its relativistic mass and thereby increasing its energy, and the difference in its energy is what is seen as its kinetic energy. So let's find out the gamma factor of this speed for this speed, and then using that we can find out the kinetic energy, which is going to tell us the potential difference that's required to this job. So gamma is given by square root of 1 over square root of 1 minus v here is 0.96 square times c square, and I'm going to divide that by c square. So c square gets cancelled out because they're present both in the numerator and the denominator. So what's left is 1 minus 0.96 squared. I have already calculated this out, so it comes out to be 3.57. So 3.57 is its gamma factor, and the corresponding kinetic energy is found out by drawing two lines, one parallel to the vertical axis and another one parallel to the horizontal axis. So it's somewhere in between 250 and 300. So I'm going to say it's 275 mega electron volts. So EK is 275 mega electron volts, and this is the amount of potential energy that's required to get this muon from rest to this speed. But we don't want the potential energy, but we just want the potential difference. So how do we do that? So we just take this energy, call it EP instead of EK, because energy is conserved and the muon is getting its potential energy. I mean, it's getting its kinetic energy from the potential energy that it had. So the potential difference that makes this potential energy possible is V. This is the capital V, which is equal to EP divided by Q, where Q is the charge on the electron and EP is given in mega electron volts. So we need to convert this into joules. How much is 275 mega electron volts in joules? So 1 electron volt is 1.6 times 10 raised to minus 19 joules, and 275 of that is just 275 times 1.6 times 10 raised to minus 19, and we have the same thing in the denominator. It gets cancelled out, so we need 275 joules to accelerate this muon from rest to a speed of 0.96 times c. So for the eighth problem, we have a flywheel which stores rotational kinetic energy in it. So this flywheel has a moment of inertia of 0.072 kg meters square, and it has an initial angular speed of 8,400 rads per second. That's radians per second. So its angular speed is what gives us the information about how much angle is being swept out each second. So that is basically telling us the rate at which this flywheel is rotating at. So in part A, they say that this rate of rotation is reduced, and this is the time in which it is reduced. We need to find out, or we need to show, that a power of 200 kilowatt was transferred during this process. So let's take a look at what power means. Power usually means the rate at which energy is being transferred. So in this case, since the only form of energy that this flywheel can have is rotational kinetic energy, the change in its energy is the change in its rotational kinetic energy. So in order for us to find out the change in rotational kinetic energy, um, we can use this expression of half I omega squared. An object with moment of inertia of I rotating at a rate of omega will have its kinetic energy, its rotational kinetic energy, to be half I omega square. Since half and moment of inertia are the common factors in both these terms, I can write it down separately. And EF is the final kinetic energy, final rotational kinetic energy. So I need to write down omega square, but yeah, the final value of omega square. It's 3,600 squared minus 8,400 squared. Divide all these terms by 9.6, the time during which this change has occurred. So I have already performed this calculation, and this gives us minus 2160 and two more zeros, or else we can also write it down as 216 kilowatts, which is very close to 200 kilowatts. But what's this minus sign in front of it? Um, this tells us whether energy is being inputted to this flywheel, or is it being taken out of this flywheel. So if it's negative, it just basically means that its final energy is less than its initial energy. So energy is um, being carried away from this flywheel. So since this flywheel is slowing down, we can say it's decelerating. So it has an angular deceleration. So when it comes to linear motion, we say a force is what creates acceleration. So an unbalanced force creates an acceleration A, and if we know how fast the velocity is changing for an object, we can find out its acceleration, then multiply it with the object's mass to get how much force the object's experiencing. So similarly, since torque is the one which creates angular acceleration, we can use this formula for torque, and then after finding out the angular acceleration, in this case the angular deceleration, and substituting that into alpha, and then we can solve this whole equation to get torque. I is already known, it's 0.072, and angular acceleration can be calculated by finding out the rate at which the angular velocity is changing. So to do that, we take the difference between the final and initial values of angular velocity, then divide that with the time in which the angular velocity changed. So I have done this as well. So the value would come out to be minus 36 Newton meters. So the reason why we are using Newton meters here is because generally torque is expressed as r times F, where r is the perpendicular distance from the pivot to the point at which force F is being applied, and F is the magnitude of force. So r is expressed in meters and F is expressed in newtons. So combining both of these things, their products would be expressed in Newton meters. Again, the negative sign is to indicate that this creates a deceleration. So it's in the direction opposite to the rotation that it already has. So calculating the number of revolutions that this flywheel makes as it slows down. So how many turns does this flywheel makes having a deceleration of alpha? So that's the question here, and we have an equation which is very much similar to a Seurat equation, which describes the displacement of an object which is undergoing an acceleration of a. But instead of using the linear terms, we have the angular terms here. So it's theta instead of s. So instead of displacement, we have the angular displacement, and instead of u, we have omega I, its initial angular velocity, times t plus 1 by 2 alpha t squared. Substituting for all these values, I get 1400 times 9.6 plus 1 by 2 and minus of this value right here. So this is the angular acceleration, or in this case deceleration, because it has minus sign in front of it. So instead of increasing the angular velocity, it decreases it. Minus sign in front of it, and 9.6 squared. So let's perform this calculation. There will be a minus sign between these two terms because alpha had a minus sign in front of it. So it's 57,600. That's not the number of revs, that's just the value of theta, your angular displacement. So it's 57,600 radians. That's the angle that's covered by this flywheel as it slows down from 8,400 to 3,600 radians per second, or else you can say it's the angle that's covered in time, 9.6 seconds. So having known this angle, we also know that one complete circle would require 2 pi radians. How many revolutions would we have for 57,600 radians instead of 2 pi? We can calculate that using this formula, x revs, and I think I have calculated something. Instead of this value, I'm going to substitute the actual value, and that comes out to be 9,167.32. So it's equivalent to 9,167.32 revs. Okay, so that's our answer for the third part in question A. Okay, so for part B of this question, they are trying to figure out if there is a way to increase the maximum energy that's stored inside of this flywheel. So we need to identify two factors that can actually increase the energy of this flywheel. So, knowing that the energy inside of this flywheel is purely rotational kinetic energy, and also knowing that the rotational kinetic energy can be written in this form, we can directly see that there are two ways of increasing it. One way is to increase the maximum or angular speed that it can have. So an increase in omega, and also we can increase the moment of inertia of this flywheel. By then that increases the angular kinetic, the rotational kinetic energy. There are actually two ways of doing this, two ways of increasing this moment of inertia. One way is to increase the total mass of this flywheel, and another way is to move this mass, or to sort of redistribute this mass so that more of the mass is now situated at the edge of this flywheel and not at the center. So mass to the edge of the wheel. So these are two ways of doing it. We have mentioned by now three factors. One is by increasing omega, which is the angular velocity of this flywheel, and another is by increasing the mass so that it increases the moment of inertia I, and another way is to move the mass to the edges. Mass to edge, so I increases, and the net effect of any of these is an increase in the rotational kinetic energy. So that solves this part as well. The ninth question is based on thermodynamics, and it describes a process where the gas is run around through three different states, and we have three different processes for this gas to go about in these three different states. X and Y are already plotted on this graph. We need to plot Z, the state Z, and then we can connect all these three dots, where each represent a state of the gas. So from this line, we know that Z comes after Y, going through a process of isobaric expansion. Isobaric expansion means there is no change in the pressure of this gas. So we have a horizontal line which indicates no change in pressure, and let Z be at that point. And we can draw a curve to connect Y and X, and also another curve to connect Z and X. We have expansion from Y to Z, another expansion from Z to X, which is an adiabatic expansion. I'm just gonna write it down for my own reference, and I'm gonna call it isobaric. So the last one is gonna be isothermal compression. Here the volume is decreasing. Isothermal compression, expansion, expansion. Okay, so numbers are not required, and we didn't have to write all these things down, the name of the processes, but I think it will be more useful for me further down the line in the same question. So we need to show that the volume of the gas at Y is 0.25 meter cube. So and also we have this multiplied by 10 raised to minus 3. Okay, and how am I going to find this out? We make use of this equation. PV at Y is equal to P times V at X. So this is from Boyle's law. We can rearrange this equation so that we get Vy to be isolated and px times vx divided by py is what we need, and substituting for all the knowns, that's pressure and volume at state x, which is 10 megapascal and 1.2 times 10 raised to minus 3, yep, meter cube. 10 megapascal times 1.2 times 10 raised to minus 3. Okay, so it's 0.10, not just 10. Divide that by pressure at y, that's 0.48 megapascal. Let's calculate this thing out. Let me clear all these previous calculations to make room for new. 0.10 times 0.2, wait, 1.2, and multiply all that and divide that by 0.48. So it's 25. Yeah, 0.25. Yep, this is what we have. It's either 25 to the power of minus 4, or it's 0.25 times 10 raised to minus 3 meter cube. Okay, so we got volume of the gas at y, and that solves this part as well. Okay, so we have solved 2 already. Moving on to part C, here it says, well, this is the equation that's stated in the first law of thermodynamics, and the first part of this question says to complete this table and use this answer box as something that can make use of for calculations. And yes, x to y is an adiabatic expansion, or is it? X to y is an isothermal compression. Change in its internal energy is 0 because internal energy depends upon temperature, and if there is no change in temperature, change in its internal energy is equal to 0. And make sure that you know that the internal energy is composed of mainly the kinetic energy of this gas, and if this gas is an ideal gas, then all of it is the total kinetic energy of the gas molecules. So here we need to subtract both of these things to get the answer, and let's do it. 262 minus 1.5, 157, 105. Okay. So 105, so 157. That's the amount of work done going from y to z. Now what about z to x? It is an adiabatic expansion, so there is no change in the heat content of the system. So everything that has performed work is obtained from the internal energy. So what about the whole cycle? So let's subtract whatever's there in this column. So we need to add them, but there is a minus sign already in front of it. So that's 74. So that's the amount of heat that's retained inside of the system after one whole cycle. And the change in internal energy is 0. And this is consistent with the first law of thermodynamics. Okay, so this part's done. And this part as well. Now we have to determine the volume of the gas at Z. So we're going to make use of this column right here because it talks about the change in state going from Y to Z or Z, if you want to call it. And since this is an isobaric process, we can make use of the work that's performed in this process, in this step, and we can write it down as P pressure, which stays the same going from Y to Z since it's isobaric. Volume is the final volume is Vz minus Vy, and what's the pressure? I believe it's 0.48 megapascals. Just gonna mention it here. Mega is 10 raised to 6, and yep, Vz stays as it is because we need to find that out. What about Vy? Vy is 1.2 times 10 raised to minus 3. And also we can substitute for W here. In this step it's 105 joules. So let's rearrange everything and calculate this Vz. Okay, we have Vz on one side. What we can do is we can perform all the calculations that's written there. Need to add it. So 0.48. Need to make sure that it's correct, and it was not. 105. Divide that by 0.48 times 10, 6. And that's our answer. So it's 1.4. 1.4 10 raised to minus 3 meter cube. What about the efficiency of this cycle? So efficiency is defined as useful output divided by the total input, and in this case it's energy, but we can also find out the efficiency if we know the input power, or well, under the output power, useful output power, that is. Okay, so Q in, wait, W out and Q in. So the work done throughout this cycle is 74 joules, and the total heat that's supplied to the system in this cycle is during this isothermal process. I'm going to substitute that to this equation. So we get 4 divided by 262, that's 0.2824. Which means 28.24%. Yep. The last part of this question is asking us why that it's not suitable, that this theoretical cycle is not suitable for practical applications. Um, One thing we can straight away notice is that it involves an adiabatic process, so we need perfect insulation to carry out adiabatic processing. And since there is also an isothermal process, the compression needs to be super slow, otherwise it could generate some heat inside of it, and that can increase or decrease the temperature. But of course, if it's compression, then it's going to increase the temperature. So isothermal process requires um, the cycle to be slow, or the process to be slow. Okay, so it's not that practical as we see. So the 12th question is about lenses. So here we have the characteristics of an image that's formed by a converging lens. It's real, so it's formed on the other side of the lens, and it's 4 times larger than the object. It's also formed 0.4 meters away from the converging lens. So this is the image distance V, and they're asking us to find out the focal length. So in order for us to find out f, we make use of this focal length formula, the one that relates the focal length, the object distance, and the image distance. So we already know the image distance v, but we don't know the object distance yet. So we need to find that out one first, and we make use of this magnification formula. M is equal to minus v by u, and m is equal to minus 4 because the image is actually larger than the object, and the object distance is 0.4. So let's rearrange this equation so that we can obtain u, which is 0.1 meters, and we can substitute that in that equation. Instead of u, we substitute 0.1, so it becomes 1 over 0.1, and simplifying this equation we get 5 divided by 0.4. But we don't need this value. We don't have to find out what this fraction is equal to. Instead of 1 over f, we need f itself, the focal length. So it's not 5 over 0.4, it's 0.4 over 5. And in the end, we get 0.08 meters, which is equal to 8 centimeters. So, yeah, that's the focal length of this converging lens. And for the second part, the converging lens is replaced now by a diverging lens. So we're going to do this right now. So since it is a diverging lens, the first ray, which is parallel to the principal axis, gets diverged as if it's being emitted from one of these principal foci. And the second ray can be drawn so that it passes through the middle of this lens, and as we can see, the rays are diverging. And we can also draw an image. Okay, the red arrow is the image of this black arrow, which is already given. So let's talk about the nature of the image that's formed. So that is what's required in this part. So the first one is that the size of the image is actually smaller than the size of the object, so it's diminished. And it's standing upright. It's not inverted. The last point is that because the image is formed along the same side as where the object's present, we say that this image is virtual. And we also know that these rays are diverging, so it cannot be projected onto a screen, so it is virtual. Okay, so that solves question 12.